Hi, this is Ms. Fitzmaurice. This video corresponds to free response number 6 in your review packet. So in this problem, we have a world-class runner, and it says this world-class runner can complete a 100-meter dash in about 10 seconds. Past studies have shown that runners accelerate uniformly for some time t, we don't know that time, and then run at a constant speed for the remainder of the race. So we're assuming that they're accelerating constantly and then running at a constant speed. In part A, we need to find a way, using our class with 11 students, to determine the acceleration and the time that it takes the runner to reach top speed. Alright, so your picture should probably look something like this. Here's our runner, and we have our 100-meter dash. We have our classmates with stopwatches, spaced out at about 10-meter intervals. And basically, where you get points is that you get 1 point for having a well-labeled diagram. And then your second point is for indicating that you will mark out, and I'll say that you will measure and mark out several distance points, okay, and explaining how you will measure them. So you could say with a meter stick, using the markings on the track, whatever, you need to explain it, and for indicating that you take, that your classmates record the time the runner is at each point. Okay, and explaining how you take the time. So, for example, you could say something like, well, each classmate will stand at a 10-meter mark. We'll mark out the 10 meters by measuring 10-meter sets with a meter stick and marking them with chalk. All the students will start as soon as the runner starts, and then record the time that the runner passes them. Okay, in part B, it says, describe the process that you would use to find the portion of the race that has uniform acceleration and the uniform acceleration. So there's two possible ways. So you can get points for one of these ways, but not for both. And one is to create an XT graph, and let's see, the portion of acceleration will be a parabola. But the portion of constant speed will be a straight line. So that's one method that you could use. The other method you could use is using the times collected by the classmates you could use V average is equal to x minus x naught over t minus t naught. In all cases, for each interval, x minus x naught will be 10 meters, and then for t minus t naught, the average for an interval will be the time at the end of 10-meter interval minus the time at beginning of 10-meter interval. Okay, so those are the two methods that you would use to identify where you have average velocity and where you have, where you have constant acceleration and where you have constant velocity. So you get 1 point for explaining with this graph that you're looking for the portion with acceleration to be like a parabola, okay? Or in the case that you're using V average, you're looking for the point at which V average is constant, and that's where your acceleration stopped. Okay, so you're going to get 1 point for this for either of these two things. Okay, you have to mention that the portion of acceleration looks like parabola and that there's straight line, and you have to mention, or you need to mention both this equation and you're looking for the point at which V average is constant, and that's where acceleration is stopped. Okay, so to find acceleration, you use the t found for where acceleration stops okay, and look at the approximate distance. Okay, so this is one method. There's going to be two methods again, and you can use x equals x naught plus VOT plus 1/2 AT squared, where x is the distance at which acceleration stopped, x naught and v naught are 0, and t is the time found at which acceleration stops. Okay, so for this you would be reading all of this off of the graph, and you can get this point if you used the graph method before. Okay. On the other hand, if you were using average velocity, then you can use A is equal to delta V over delta T, and you use the time found before, and you use the maximum or final v found for any interval. So again, there's one point for either one or the other. And there's actually 2 points associated with this, one for describing and one for indicating either this equation or this equation. So there's 2 points total. One goes with the explanation, one goes with the equation. Part C is a little bit more straightforward. It says after collecting data, you observed that the first 10 meters are covered in 2 seconds, okay, who starts from rest and accelerates with a constant acceleration. The remaining 90 meters are run with the same velocity the sprinter had after 2 seconds. And so we want to first determine the sprinter's constant acceleration. And we can use our first kinematics equation, x equals x naught plus v naught t plus 1/2 at squared. So you get 1 point for just writing that equation down, and then 1 point for solving correctly. And the correct solving x naught and v go away. We have 10 meters, because that's how far you are after 2 seconds, is 1/2 times a times 2 squared. You can solve for a and you get 5 meters per second squared. So you get a second point for correctly solving. In part D, or sorry, that was not part D, that was C. So in C part 2, it asks you to find the sprinter's velocity after 2 seconds. So you can use v equals v naught plus a t. You know that v naught is 0. And for correctly plugging in your answer to this third equation, so if you got your answer wrong to part 1, but you plugged it in correctly underneath the a and then multiplied by 2, that is where the point is. So you get 10 meters per second. So there's 1 point associated with this, but it's for correctly plugging your answer from 1 into 2. And then in part 3, it asks you to find the total time needed to run the full 100 meters. Well, we know that t total will be 2 plus the time needed to run the last 90 meters. You could call it whatever you want. I'm going to call it T90. So for some kind of expression where you're adding a total time, the 2 that you had for the first 2 seconds plus the total time to run the remaining 90 meters, that is 1 point. Now, to find T90, you need the first equation. So you have x90 is equal to x naught, which is 10, plus v naught t 90 plus 1/2 a t90 squared. Of course, x naught is 10, and you have 90 equals 10 plus, 100. You end up at the 100 mark, plus 10, the v naught t, and you end up with t is equal to 9 seconds. And so you can get your total t, and you end up with 11 seconds. So you get a second point for correctly substituting and solving for T90 is 9 seconds. Finally, in part D, they show you these 2 graphs, and it says that in this situation, there's 4 world-class runners. They all accelerate at different rates but reach the finish line at the same time. Okay. Now, what they're asking you is, they're saying one of these two graphs is incorrect. Tell us which one. And the answer is that the VT graph is incorrect. So for identifying correctly that the VT graph was the one that was incorrect, you get 1 point. And the reason is this, that x is, or displacement is, the area of a VT graph. And basically, because the four lines always have different area, they can't reach the finish line at the same time. Okay, so the last point is for somehow relating it to the fact that delta x is the area of a VT graph.